Welcome to this problem walkthrough. In this session, we'll explore problem number 1943, describe the painting. We'll break down the problem step by step, analyze different approaches, and ultimately work toward an efficient solution. Let's dive right in. In this problem, you're tasked with describing a painting that is built using a series of segments. Each segment is represented as an array containing three values: the starting point, the ending point, and the color of the segment. The start point is inclusive, meaning the segment starts at this position, while the end point is exclusive, meaning the segment stops just before this position. Initially, the canvas is blank, with no colors applied to any position. As you add new segments, they may overlap with segments that are already painted. In those cases, the color of the new segment takes precedence and overwrites the colors in the overlapping region. Any areas that don't overlap will keep their original colors. Your goal is to return a concise description of the final painting, where the canvas is represented as a series of non-overlapping, continuous segments sorted by their starting points. It's important to note that even if two adjacent segments share the same color, they should remain separate and not be merged in the output. To better understand the problem, let's consider an example. Suppose you are given the input segments 1, 4, 5, 4, 7, 8, 1, 5, 7. Initially, the canvas is blank. After applying the first segment, 1, 4, 5, the range from 1 to 4 is painted with color 5. Next, the segment 4, 7, 8 is added, which paints the range from 4 to 7 with color 8. Note that this does not affect the earlier segment since there is no overlap. Finally, the segment 1, 5, 7 is applied. This segment overlaps with both of the earlier segments. It overwrites the range from 1 to 4 with color 7, and it also overwrites part of the second segment, specifically the range from 4 to 5, with the same color 7. The result is a canvas described by three distinct segments: 1, 4, 7, 4, 5, 7, and 5, 7, 8. These segments are non-overlapping, and adjacent segments with the same color remain separate. Now let's look at another example. Suppose the input segments are 1, 10, 1, 2, 5, 2, 6, 9, 3. Initially, the canvas is blank. When the first segment is applied, the range from 1 to 10 is painted with color 1. Then, the second segment, 2, 5, 2, is added. This segment partially overlaps with the first one. The range from 2 to 5 is overwritten with color 2, while the ranges from 1 to 2 and 5 to 10 remain painted with color 1. Finally, the third segment, 6, 9, 3, is added. This segment partially overlaps with the range from 5 to 10, so the range from 6 to 9 is overwritten with color 3, while the ranges from 5 to 6 and 9 to 10 retain the original color 1. The final result is described by 5 distinct segments: 1, 2, 1, 2, 5, 2, 5, 6, 1, 6, 9, 3, and 9, 10, 1. Breaking this down further, after processing all the segments, the canvas is divided as follows. The range from 1 to 2 retains the original color 1 because it was never overwritten. The range from 2 to 5 is painted with color 2, as the second segment overwrote the initial color. The range from 5 to 6 remains painted with color 1, as it was unaffected by later segments. The range from 6 to 9 is painted with color 3, as the third segment overwrote the previous colors in this region. Finally, the range from 9 to 10 retains color 1, as it was not overwritten. This gives us the final output of 1, 2, 1, 2, 5, 2, 5, 6, 1, 6, 9, 3, 9, 10, 1. There are several important constraints and edge cases to consider when solving this problem. First, if there is only one segment, the output should simply match the input segment because no overlaps occur. For example, the input 1, 3, 4 results in 1, 3, 4. In cases where segments do not overlap, the output should be the sorted input. For instance, 1, 2, 5, 3, 4, 6 produces 1, 2, 5, 3, 4, 6. When a segment fully overwrites another, only the overwriting segment appears in the output. For example, 1, 5, 3, 1, 5, 4 produces 1, 5, 4. Lastly, the solution must handle up to 50,000 segments efficiently and ensure that adjacent segments with the same color remain separate. For example, 1, 3, 5, 3, 5, 5 results in 1, 3, 5, 3, 5, 5, as merging them would violate the problem constraints. When tackling this problem, a natural starting point is the brute force approach. The intuition behind this method is to simulate the painting process directly. For each segment, we iterate through all the points in its range, assigning the specified color to each point. Once all segments are processed, we can identify the colored intervals by traversing the points sequentially. To implement this, we could use an array or hash map to keep track of the color assigned to each individual point. However, this approach comes with significant drawbacks. The time complexity is proportional to the total number of points covered by all segments, which can become prohibitively expensive for large inputs. Additionally, the space requirement grows with the number of unique points, leading to inefficiencies when intervals are large or overlap extensively. These limitations make the brute force method impractical for this problem, especially when dealing with large datasets. A more efficient solution is the sweep line algorithm. The key insight here is that the problem can be simplified by focusing only on the segment boundaries, the start and end points of each interval, since these are the only locations where changes in color occur. By treating these boundaries as events, we can determine the resulting intervals without processing every individual point. The approach involves representing each segment as two events, a start event that adds a color and an end event that removes it. Once we have all the events, we sort them by position. If two events share the same position, we prioritize end events to avoid processing overlaps incorrectly. From there, we sweep through the sorted events, maintaining a running sum of active colors. Whenever the active color changes, we record the interval that just concluded. This approach allows us to efficiently capture the intervals with distinct colors while avoiding the inefficiencies of the brute force method. To implement the sweep line algorithm, we process the sorted events step by step. As we iterate through the events, we maintain two key variables, the current position and the running sum of active colors. Whenever there is a gap between the previous position and the current one, and the active color is non-zero, we know we have a valid interval to record. This interval captures the range where the active color was consistent. After recording the interval, we update the running sum with the change in color at the current event and move to the next position. By the end of this process, we will have constructed the complete list of distinct color intervals. In terms of complexity, sorting the events requires O(n) log n time, and the single pass through the events is O(n), making this approach highly efficient. It is not only faster than brute force but also elegant in its handling of overlapping segments. The sweep line algorithm is the clear choice for solving this problem. By focusing only on the critical points, the start and end of each segment, we minimize unnecessary computation and achieve significant performance gains. The insight that color changes occur only at these boundaries was the turning point in arriving at this strategy. While the algorithm does require sorting the events, this added complexity is negligible compared to the inefficiency of iterating over every point, as in the brute force approach. One trade-off is that the sweep line algorithm is slightly more complex to implement, but this is outweighed by its scalability and efficiency, especially for large datasets. Ultimately, the sweep line algorithm enables us to solve the problem in a way that is both computationally efficient and conceptually clear, making it the optimal solution. In this problem, we are tasked with determining the final color of each point on a canvas after applying a series of painting commands. Each command specifies a range, defined by a start and end point, along with the color to be applied to that range. Importantly, if commands overlap, the later commands overwrite the colors of the earlier ones. To solve this, we start with a brute force approach. First, we initialize a list called canvas, which represents the entire range of points that can be painted. The size of this list should be large enough to cover the maximum range specified in the commands. Initially, all elements of the canvas are set to a default value, such as 0, to indicate that no painting has occurred. Then, for each command, we iterate through the specified range and update the corresponding indices in the canvas with the given color. This straightforward approach ensures that each point is painted correctly based on the commands provided. Once all the commands have been processed, the canvas list will contain the final color of each point. This list serves as the output, representing the painted state of the canvas after all commands have been applied. To understand this better, consider the example where we have the commands 1, 5, 3, 2, 6, 4, 0, 2, 2. First, we determine the maximum range needed, which is 7 in this case, as the highest endpoint is 6. We then initialize the canvas list to 0, 0, 0, 0, 0, 0, 0, where all points are unpainted. This setup allows us to simulate the painting process step by step and observe how each command updates the canvas. Now, let's process the commands one by one. For the first command, 1, 5, 3, we paint the indices from 1 to 4 with the color 3. The canvas is updated to 0, 3, 3, 3, 3, 0, 0. Next, with the command 2, 6, 4, we overwrite the indices from 2 to 5 with the color 4. This changes the canvas to 0, 3, 4, 4, 4, 4, 0. Finally, the command 0, 2, 2 paints the indices from 0 to 1 with the color 2, resulting in the final canvas of 2, 2, 4, 4, 4, 4, 0. This updated list reflects the correct colors at each point after applying all the commands in the given order. This example highlights several key insights about the brute force approach. First, the overriding logic is naturally handled by directly updating the canvas during each command's iteration. Later commands automatically replace earlier colors in overlapping regions. However, this approach can become inefficient for large input sizes since the time complexity depends on the sum of the lengths of all ranges. This makes it proportional to sum of ranges. Additionally, we must consider edge cases, such as when there are no commands, where the output should remain the initial canvas. In cases of fully overlapping commands, the last command should dictate the final color, while non-overlapping commands should affect only their designated regions independently. Handling these scenarios correctly ensures the solution is robust and accurate. To implement this approach, we rely on two main data structures. The canvas list represents the range of points, where each index corresponds to a specific point, and its value indicates the color. This structure allows for straightforward updates during the processing of commands. The second data structure is the list of commands, where each command is a triplet: start, end, color. While the brute force method is simple, it can be optimized in specific cases. For instance, if the range is very large but most points remain unpainted, we could use a sparse representation, such as a dictionary, to store only the painted segments. For even more advanced scenarios, a segment tree could be employed to efficiently handle range updates in queries. In terms of complexity, the brute force approach has a time complexity of sum of ranges, and a space complexity of max range, making it suitable for smaller scale problems but potentially inefficient for larger ones. These optimizations provide a pathway to balance simplicity and performance depending on the problem constraints. Here, we start by importing the defaulted class from the collections module, which will help us manage the changes in color efficiently. Then, we define a class called solution, and within it, a method named split painting that takes a list of segments as input. Each segment contains three values: the start point, the end point, and the color applied to that segment. The key idea is to use a sweep line algorithm to track the changes in color at specific points. To accomplish this, we initialize a defaulted named changes to store how the color values change at different points. For every segment in the input, we increment the color value at the start point and decrement it at the end point. This way, we mark where a color begins and ends. After processing all segments, we sort the keys of the changes dictionary to process the points in ascending order. This ensures that we evaluate the segments in the correct sequence. We then initialize an empty list called result to store the final painted segments, a variable current_color to keep track of the cumulative color value at any given point, and a prev_point variable to remember the previous position as we iterate through the sorted points. The for loop begins to iterate over these sorted points, and at each step, we check if prev_point is not none and if current_color is greater than 0. If both conditions are true, we append a new segment to the result list that spans from prev_point to the current point and is painted with the current color value. Next, we update the current_color by adding the change in color at the current point, which was recorded earlier in the changes dictionary. This ensures that the cumulative color value reflects the segments currently being applied. After updating the color, we set the prev_point variable to the current point to prepare for the next iteration. Finally, once all points have been processed, we return the result list, which contains all the segments of the painting along with their respective color values. This approach ensures that we efficiently compute the painted segments without redundantly iterating over the entire range of the painting. By leveraging the sweepline algorithm and the defaultIt, we achieve an optimal solution to the problem. Here, we begin by importing the necessary Java utilities and defining our solution class. Within it, we create the split painting method, which accepts a 2D array of segments. First, we use a tree map to store the points where changes in color intensity occur. The tree map is useful because it automatically maintains the keys in sorted order, which is crucial for processing these points sequentially later. Next, we iterate over each segment in the input. For every segment, we extract the start point, end point, and the color value. At the start point, we increment the color intensity in the tree map, and at the end point, we decrement it. These changes allow us to keep track of how the color intensity evolves over the range of the painting. After recording these changes, we initialize a result list to store the final segments, as well as variables to track the previous point and the current color intensity. These will help us construct the result as we process the points in the tree map. Now, we iterate through the tree map entries, which represent the sorted points where changes occur. For each entry, we first check if the previous point is valid and the current color intensity is greater than 0. If so, we add a new segment from the previous point to the current point, including the accumulated color intensity. This ensures that we only include segments where the painting is visible. Next, we update the current color intensity by adding the value at the current point and set the previous point to the current point. Finally, after processing all the points, we return the result list, which contains the non-overlapping segments with their respective color intensities. This approach is both efficient and elegant, as the tree map structure allows us to handle the problem's requirements in a clean and orderly manner. In this first example, we have 3 segments, 1, 4, 5, 4, 7, 7, and 1, 7, 2. We start by initializing a changes dictionary to track the color changes at the segment boundaries. This allows us to efficiently calculate the overlapping colors. For the first segment, we add 5 at the start point, 1, and subtract 5 at the end point, 4, resulting in changes equals 1, 5, 4, minus 5. For the second segment, we add 7 at 4 and subtract 7 at 7, updating changes to 1, 5, 4, 2, 7, minus 7. Lastly, for the third segment, we add 2 at 1 and subtract 2 at 7, giving us a final changes dictionary of 1, 7, 4, 2, 7, minus 9. Next, we sort the keys of this dictionary to process points in order, resulting in sorted_points equals 1, 4, 7. From here, we initialize current_color to 0, prev_point to none, and an empty list for our result. Using a sweepline algorithm, we process each point. At point 1, since there's no previous point to evaluate, we simply update the current_color to 7. At point 4, we add the segment 1, 4, 7 to the result and update the current_color to 2. Finally, at point 7, we add the segment 4, 7, 2 to the result and reset the current_color to 0. This gives us the final result for the first example, 1, 4, 7, 4, 7, 2. Now, let's consider a second example, where the segments do not overlap. The input segments are 1, 3, 4, and 3, 5, 6. Again, we begin by initializing a changes dictionary. For the first segment, we add 4 at 1 and subtract 4 at 3, resulting in changes equals 1, 4, 3, minus 4. For the second segment, we add 6 at 3 and subtract 6 at 5, updating the dictionary to changes equals 1, 4, 3, 2, 5, minus 6. Sorting the keys gives us sorted_points equals 1, 3, 5. Using the sweepline algorithm, we process these points. At point 1, we update current_color to 4, as there's no previous segment to add. At point 3, we add the segment 1, 3, 4 to the result and update current_color to 2. Finally, at point 5, we add the segment 3, 5, 6 to the result and reset the current_color to 0. The result for this example is 1, 3, 4, 3, 5, 6, which represents two non-overlapping segments. Now, let's explore the third example, where segments are fully nested within each other. The input segments are 1, 5, 3, and 2, 4, 2. We start by initializing the changes dictionary. For the first segment, we add 3 at 1 and subtract 3 at 5, resulting in changes equals 1, 3, 5, minus 3. For the second segment, we add 2 at 2 and subtract 2 at 4, updating the dictionary to changes equals 1, 3, 2, 2, 4, minus 2, 5, minus 3. After sorting the keys, we get sorted underscore points equals 1, 2, 4, 5. With the sweep line algorithm, we process these points to construct the result. At point 1, we initialize current underscore color to 3. At point 2, we add the segment 1, 2, 3 to the result and update current underscore color to 5, as the segment from 2 to 4 adds an additional 2 to the color. At point 4, we add the segment 2, 4, 5 to the result and update current underscore color to 3, as the subtraction of 2 reduces the color. Finally, at point 5, we add the segment 4, 5, 3 to the result and reset current underscore color to 0. The final result for this example is 1, 2, 3, 2, 4, 5, 4, 5, 3, showing how the nested segments contribute to the overall painted intervals. To analyze the time complexity of our solution, we can break it down into 3 main steps. First, we record the changes in the changes dictionary. This involves iterating through the segments list, which contains n segments. For each segment, we perform 2 operations on the dictionary, adding the color value at the start point and subtracting it at the end point. Since each of these operations takes constant time, the total complexity for this step is O(n). Next, we sort the keys of the changes dictionary. If there are k unique keys, sorting them requires O(k*log k) time. Finally, we process the sorted points. This involves iterating through the sorted keys and performing constant time updates to maintain the current color and create result segments when necessary. This step takes O(k) time. These components give us a clear breakdown of the time complexity for each part of the algorithm. Combining all these steps, the total time complexity of the solution can be summarized as follows: O(n) for the initial processing of segments, O(k*log k) for sorting the unique keys, and O(k) for iterating through the sorted points. Adding these together, the overall time complexity becomes O(n) plus k*log k, where n is the number of segments and k is the number of unique points. Now, for space complexity, let's start with the changes dictionary. This dictionary stores at most 2n keys, corresponding to the start and end points of each segment. However, the actual number of unique keys is k, where k is bounded by 2n. As a result, the memory usage of the dictionary is proportional to the number of unique keys, resulting in O(k) space. Next, there's the sorted underscore points list, which contains the sorted keys of the changes dictionary. Since it only holds these unique points, it also uses O(k) space. Additionally, we need to account for the space used by the result list, which stores the output segments. In the worst case, there could be k1 segments, where each segment corresponds to a pair of consecutive unique points. This results in O(k) space for the result list. Combining all these components, the overall space complexity of the solution is O(k). When we analyze the best, average, and worst cases, we see that in the best case, the number of unique points k is minimal, such as when all segments start and end at the same points. Here, the sorting step becomes trivial, leading to a time complexity of O(n) and a space complexity of O(k). In the average case, the points are moderately distributed, and the time complexity remains O(n) plus k*log k, with space complexity still O(k). In the worst case, where all start and end points are unique, the number of unique points k equals 2n. This results in a time complexity of O(n) plus 2n*log 2n, which simplifies to O(n*log n, and a space complexity of O(n). Now, let's compare this approach to a brute force method. A brute force solution would involve iterating through each segment and explicitly constructing the painted regions. This requires repeatedly checking for overlaps between segments, which is computationally expensive. For n segments, this approach could take n squared time in the worst case due to the overlap checks. In contrast, our sweepline algorithm avoids these costly overlap checks by maintaining a cumulative color change at each unique point. This reduces the time complexity to n plus k asterisk log k. To prove this mathematically, we note that the dominant term in the time complexity is the sorting step, which takes k asterisk log k. Since k is at most 2n, we can bound this term as n asterisk log n. The other steps, such as processing the segments and iterating through the sorted points, contribute n. Therefore, the overall time complexity simplifies to n asterisk log n in the worst case. Memory usage, being proportional to the number of unique points k, results in a space complexity of k. When working on problems like describe the painting, one common mistake is failing to account for overlapping ranges. For instance, if you're painting overlapping segments and overwrite previous values without considering their intersections, you risk losing earlier modifications, leading to incorrect results. To avoid this, data structures like segment trees or sweepline algorithms can be used to handle overlaps effectively. Another frequent issue is relying on inefficient brute force implementations. Iterating over each point in a range for multiple queries may seem straightforward, but it often results in poor performance, especially for large inputs, causing time limit exceeded errors. Instead, optimize using data structures such as Fenwick trees, segment trees, or lazy propagation to reduce complexity. Lastly, it's critical to handle edge cases. Forgetting scenarios such as empty ranges, single-point ranges, or queries that extend beyond the valid domain can lead to runtime errors or incorrect answers. Carefully analyzing constraints and explicitly addressing these edge cases in your code can help ensure your solution is robust. Another challenge arises with the incorrect handling of query order. If the problem specifies that operations must be processed sequentially, failing to maintain this order can lead to inconsistent or invalid results. To address this, ensure that operations are applied in the correct sequence, which may involve sorting the queries or simulating them step by step. Additionally, many developers overcomplicate their solutions by jumping straight into advanced techniques without fully understanding the problem. This often leads to unnecessary bugs or inefficiencies. A better approach is to begin with a simple brute force or simulation method, verify its correctness, and then incrementally optimize as needed. This helps maintain clarity and reduces the chances of introducing errors. To excel in interviews, it's essential to fully understand the requirements of problems like this one. Determine whether overlapping ranges, cumulative effects, or order-specific operations are key factors, as these nuances often dictate the choice of data structures. For example, if the naive solution exceeds n log n in complexity, consider more efficient options like segment trees, binary index trees, or sweepline algorithms. Testing edge cases is another vital step. Ensure you include scenarios like empty input, minimal ranges, and maximum constraints during validation. Be prepared to discuss trade-offs between space and time. For instance, while segment trees allow faster query handling, they require additional memory. Lastly, even if you use an advanced approach, always be ready to explain simpler methods and why they may fail for larger inputs. This demonstrates both your depth of understanding and your problem-solving flexibility. Understanding related problems can significantly enhance your ability to tackle interval-based challenges. For example, LeetCode 7.15, the range module, involves adding and removing intervals while handling range queries efficiently, a concept closely tied to this problem. LeetCode 10.94, carpooling, emphasizes managing overlapping intervals, often solved using a sweepline approach. In LeetCode 2.53, Meeting Rooms 2, the focus shifts to finding the maximum number of overlapping intervals, which helps build intuition for scenarios requiring interval counting. Lastly, LeetCode 3.70, Range Addition, is a simplified version of range updates that uses the difference array technique. Exploring these problems can deepen your understanding of common patterns and strategies for solving interval-based questions. There are several alternative approaches to solving problems like this, each with its own trade-offs. For example, the difference array is simple to implement and reduces the time complexity for range updates to 1. However, it's limited to cumulative operations like addition or subtraction. A segment tree with lazy propagation, on the other hand, is highly efficient for dynamic range updates and queries, operating in log n. The downside is that it requires additional space and is more complex to implement. The sweepline algorithm is another powerful option, particularly for problems where the order of events matters. It's efficient but can be less intuitive and harder to debug, especially for beginners. Finally, brute force simulation offers simplicity and ease of understanding, but it's often inefficient for large inputs, leading to time limit exceeded errors in competitive programming. Choosing the right approach depends on the problem's constraints and the trade-offs you're willing to make in terms of complexity, space, and time. Great job reaching the end of this problem walkthrough. To summarize, we explored the describe the painting problem, reviewed a brute force approach, and highlighted key takeaways for interval-based problems. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!